Hello, everyone. Hello, everyone. In this video, we're going to talk about related rate problems. So to solve related rate problems, first draw a picture, make a list of all the known and unknown rates and quantities, relate the variables in an equation, then differentiate this equation with respect to time, and finally, substitute the known quantities and rates and solve for the unknown quantity. So for this first problem, we have the width of a rectangle is increasing at a rate of 2 centimeters per second. Its length is increasing at a rate of 3 centimeters per second. And we want to know at what rate is the area of the rectangle increasing when its width is 4 centimeters and its length is 5 centimeters. So we'll draw a picture. We'll label the sides width and length. And we know that the area is the length times the width. We're given that the rate of change of the width with respect to time is 2 centimeters per second. The rate of change of the length with respect to time is 3 centimeters per second. And then we want to know the rate of change of the area with respect to time when the width is 4 centimeters and the length is 5 centimeters. Okay, so we'll go ahead and we'll use this equation, area equals length times width. We'll differentiate this with respect to time. So we have dA dt on the left-hand side. On the right-hand side, we have to use the product rule. So we'll do the derivative of the first times the second plus the first times the derivative of the second. We can now go ahead and substitute in the quantities. We know that dL dt is 3. W is 4, L is 5, and dW dt is 2. And we have 3 times 4, which is 12, plus 5 times 2, which is 10, giving us 22 centimeters per second, centimeters squared per second as the rate of change of the area with respect to time. For the next problem, a police car is approaching a right-angled intersection from the north. That means the police car is moving that way. It's chasing a speeding car that has turned the corner, is now moving straight east, so that's moving that way. When the police car is 0.6 miles north of the intersection, the car is 0.8 miles to the east. The police determines with a radar gun that the distance between them and the car is increasing at 20 miles per hour. So let's go ahead and label these sides. We'll call this side Y, this side X, and the distance between them we'll call R. Okay, if the police car is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? Okay, so we're given that when Y equals, the police car is 0.6, X equals 0.8, and the distance between them, which is dr dt, the distance between them is changing at a rate of 20 miles per hour. Okay, we also know that the police car is moving at 60 miles per hour towards the intersection. So that's going to be negative 60 miles per hour. And what we want to find is the speed of the car. So that's going to be dx dt. Okay, so there's one more piece of information that we'll need here. When y is equal to 0.6 and x is equal to 0.8, we can calculate what the r is using the Pythagorean theorem. So we'll have r squared equals x squared plus y squared. And so we'll go ahead and substitute in these values. We have 0.8 squared plus 0.6 squared, which is 0.64 plus 0.36, which is equal to 1. So r is equal to 1 when y is 0.6 and x is 0.8. This actually is the equation that we're going to use also. So x, just rewriting it over here, x squared plus y squared equals r squared. We'll now differentiate this with respect to time. So this becomes 2x dx dt plus 2y dy dt. And over here we have 2r dr dt. Okay, we can now substitute in the known quantities. X is 0.8, We want to find dx dt. Y is 0.6. dy dt is negative 60. R is equal to 1. And dr dt is 20. Okay, so we just need to solve for the dx dt. I'll take a few steps here. Plus, this actually becomes minus because of the negative sign here. And this is 72. And this equals 40. So that when we solve for dx dt, we add 72 to both sides, we get 112 divided by 1.6. Which is equal to 70 miles per hour. Okay, for the next problem, we're looking at the angle of elevation. A rocket lifts off at the Kennedy Space Center in Florida. Camera is placed 2,000 feet away. The rocket is taking off there. The height of the rocket is given by this equation, 50t squared. And the question asks to find the rate of change in the angle of elevation of the camera 10 seconds after liftoff. The angle of elevation, if we draw a line here, is given by this angle here. So we can use the Pythagorean theorem to find this hypotenuse, just in case we might need that. R, which will be a function of t, is going to be the square root of 2,000 squared plus 50 t squared squared. So we'll just keep that aside. So we're looking for the rate of change of the angle of elevation. We have the opposite side and the adjacent side. We'll go ahead and use a tangent. We know that the tangent of theta is equal to that opposite side, 50t squared, over the adjacent side, 2,000. And that's our controlling equation. We can now differentiate this with respect to time. So we'll use the chain rule here. We'll get the secant squared of theta, and then we multiply that by the d theta dt. On the right-hand side, we get 100 t over 2,000. Cancel some of these out, so we get t over 20. We want to solve for d theta dt, the rate of change of the angle of elevation. This is going to be t over 20 divided by the secant squared, but 1 over the secant squared is equal to the cosine squared, so we'll just say t over 20 times the cosine squared of theta. So for the cosine, we'll just look at the triangle here. The cosine is equal to the adjacent angle, the adjacent side divided by the hypotenuse here. So the cosine of theta is going to be equal to 2,000 over our r of t here, which is in 2,000 squared plus 50t squared squared. So we'll put that in here. So at t equals 10 seconds, we'll go ahead and put that in there, and then we'll have the cosine squared, which is this. So we'll have 2,000 over the square root of 2,000 squared plus 50 times 10 squared, which is 100. So that'll be 5,000, and we'll square that. And then we'll go ahead and solve that. And if we punch that into the calculator, we'll get, well, this is squared here. We'll get 2 over 29, and the units are radians per second. The rate of change of the angle of elevation is 2 over 29 radians per second. Okay, so we have water running into a conical tank at the rate of 9 cubic feet per minute. So that means the rate of change of the volume of water in the tank will be 9 cubic feet per minute. The tank stands point down, has a height of 10 feet. So that's this distance here. This is 10 feet. And a base of 5 feet right here. We want to know how fast the water level is rising when the water is 6 feet deep. So we'll call this the height h, and we'll call this the radius here of the water, like that. Okay, we can use similar triangles in here. So we have two triangles. We have a little triangle here, and we have the bigger triangle here. And since they're similar, we know that the ratio of the side lengths is equal. So r over h is equal to 5 over 10, or solving for r, we get that r is equal to 1/2 h. We're given the volume, the formula for the volume, it's 1/3 pi r squared h. We could go ahead and make that substitution now. 1/3 pi r is equal to 1/2 h. So we'll just substitute that in here. We have to square that h. And then we get, when we square this, we'll get 1/4 times the 1/3 gives us 1/12. We'll have pi, and then we'll have h squared times h, so that's h cubed. Okay, we'll go ahead and differentiate this with respect to time. So we'll get dv dt is equal to 1/12 pi times 3h squared dh dt. We want to solve for dh dt. We want to know how fast the water level is rising when the water is 6 feet deep. So that is when the h is equals to 6 feet. So we'll go ahead and substitute these quantities in. We know dv dt is 9. We have, we'll go ahead and cancel here. So 3 divided by 12 gives us 1/4. We'll have pi, h squared, so that'll be 6 squared. And then we have dh dt. This will be 6 squared is 36. 36 divided by 4 is 9. So I'll have 9 pi. 9 equals 9 pi dh dt. And finally, we'll solve for dh dt. And we'll get 1 over pi. And the units on this will be feet per minute. That's the answer. And that's it.